Hi, welcome back to Calculus. Today we're looking at section 4.5, indeterminate forms, and L'Hopital's rule. So L'Hopital, fun looking name to try and spell and say. Anyway, the idea here is this: we're going to be looking at some limits that we couldn't previously evaluate. We can now because we have derivatives, but it's going to take L'Hopital's rule to do it. So for instance, let's look at this function f of x. F of x here is x minus sine x over x. If we try to take the limit as x goes to 0 here, this is going to be undefined because the bottom is 0. You can't plug it in. But if we look closer, if you plug 0 into the top, you actually have 0. The sine of 0 is 0. So we end up with 0 over 0. And this is really important. That's what's called an indeterminate form, 0 over 0. We're going to be able to make this work with infinity over infinity as well. We'll talk about that in just a minute. But 0 over 0 is the setup to use L'Hopital's rule, which I wrote down over here. This is L'Hopital's rule. Suppose f of a equal to g of a is equal to 0. So, right, that's the scenario we have here. The top and the bottom both equal 0 if we plug in that 0. And f and g are differentiable on an interval I containing a, and the bottom is not, the derivative of the bottom is not equal to 0 on that interval. Then, the limit as x approaches a of f of x over g of x is equal to the limit as x approaches a of f prime of x over g prime of x. Now, this is really nice and really important that you hear this. Notice it's just the derivative of the top piece over the derivative of the bottom piece. Even though we have a quotient, we're not using a quotient rule. We're not taking the derivative of this whole thing in one big piece. We're going to be taking the derivative of the top, derivative of the bottom, and just taking that limit of those two derivatives on top of each other. So let's go ahead and take a look. We'll look at this example first, and then we'll do a few others. So, hey, let's try L'Hopital's rule. Okay, so I just put on the board the first example that we already kind of looked at just briefly, and I worked it out this time using L'Hopital's rule. So importantly, again, it's a 0 over 0. If we plug in 0 on the top and plug in 0 on the bottom, both of them are 0. That means we can use L'Hopital's rule. So what I did is I just took the derivative of the top. So the derivative of x is 1, derivative of minus sine x is a minus cosine x, and on the bottom the derivative of x is 1. Now we can plug in 0. That's not going to be a problem. The bottom's just a 1, so we can plug this 0 in. Cosine of 0 is 1, so 1 minus 1 over 1 is 0. There, we found the limit. Not so bad. Let's do another one. I've got more. Alright, so here's our next example. The limit as x goes to 0 of x cubed over 1 minus cosine x. Again, if you plug in 0, 0 cubed is 0. Cosine of 0 is 1, so 1 minus 1 is also 0. This is a 0 over 0 form. So we'll take our derivatives. On the top, we get 3x squared. On the bottom, the 1 disappears. Derivative of negative cosine is a positive sign. But again, if we try 0 here, we have a problem. We get 0 on the top and 0 on the bottom because the sine of 0 is 0. Guess what? That just means we do it again. So we're going to take those derivatives top and bottom again and see if this ever works itself out. Hopefully, this one's going to. They don't all, but hopefully, hope this one does. So I take the derivative again. Derivative of 3x squared is 6x. Derivative of sine is cosine. And now we can see that if we plug in 0 for cosine, we get 1. So we don't have 0 over 0 anymore. So I plug it in. 6 times 0 over cosine 0 is 0 over 1. And our limit is 0 again. All right. Let's see. I've got more. We're just going to do some more examples. All right. So here we go. Here's another example. This one's definitely a bigger mess. We have the limit as x goes to 0 of the square root of 1 plus x minus 1 minus x over 2 all over x squared. If you trust me, when you plug in 0 for all these x's, you get 0 over 0. If you don't trust me, go back and plug them in yourself and see that it works, or doesn't work rather, I guess. So I need to take the derivative. When I do that, the bottom is nice. The derivative of x squared is 2x. The minus 1's going to go away when I take its derivative. The minus x over 2, that's just like a minus 1/2 x. So that turns into a minus half. The only real interesting bit is this square root of 1 plus x. So I would encourage you to go back and take that derivative, make it 1 plus x to the half power, and then drop the exponent, subtract 1, all that kind of good stuff. You'll get 1 over 2 times the square root of 1 plus x. Unfortunately, if we plug in 0 here, we end up with a half minus a half on the top, that's 0, and 2 times 0 on the bottom, also 0. So we have to take our derivative again. The good news is we can see what's going to happen here. The derivative on the bottom is 2. That's not going to be 0. So we're definitely going to be someplace after this one. The derivative of the top, the half drops out, and again, take this derivative. I would recommend rewriting it as 1/2 times 1 plus x to the negative half power, and then taking its derivative. If you do, you get a negative 1/4, or negative 1 over 4 times 1 plus x to the 3/2 power, all over 2. So then I plugged in 0, I have 1 plus 0, which is 1. 1 to any power is 1, so that's just a negative 1/4 over 2, which is the same as negative 1/4 times a half, and there's our limit. It's negative 1/8. All right, so now we're going to go into some other indeterminate forms, and we're going to see a little bit about what happens with those. So let's do this. All right, so I have a couple more indeterminate forms on the board here, and then we'll look at some examples. The other indeterminate forms are infinity over infinity, infinity times 0, and infinity minus infinity. That last one is definitely the hardest of the bunch, because we really need to have things as 0 over 0. The other two are kind of straightforward. Infinity over infinity, we basically get to cheat just a little bit. We don't really even have to do much of anything, because infinity over infinity, if you take both of those reciprocals, hey, that's fun, which is allowed, you can do that. Basically we're flipping them to the other, both of them to the other side of the fraction. So the infinity on the bottom comes to the top, and the one at the top goes to the bottom. But 1 over infinity is going to be 0. So really, if you have infinity over infinity, you have just a disguised form of 0 over 0. And so we can make L'Hopital's rule work with that as well. And then for infinity times 0, again, thinking of infinity, that infinity times 0 would be the same as 0 over the reciprocal of that infinity. And that's 0 again. So we have to be able to have these in the right form so we have 0 over 0. So let's take a look at some examples. Alright, so for my next example, we want the limit as x goes to pi over 2 from the left of secant x over 1 plus tangent x. These both go to infinity. If you need to, check out the graph and you'll see it. They both have vertical asymptotes at pi over 2, and they both, as you come in from the left, are shooting up to positive infinity. So that doesn't work for us, so we take our derivatives. Derivative of secant x is secant x tangent x. Derivative of 1 plus tangent x is just going to be secant squared x. The 1 drops out, which is nice. And then I had to do a whole bunch of rearranging here, because this still looks like a mess, and it is. And this would still be infinity over infinity. But a closer examination reveals that we can get rid of some of this stuff. So we have secant over secant squared. Right away I can get rid of one of those and just have tangent over secant. But tangent is the same as sine over cosine, so I could have sine over cosine times 1 over secant since it's on the bottom. But secant is the same as 1 over cosine, so this is sine over cosine times cosine over 1. Again, since secant's on the bottom, it's going to flip and be cosine on the top, which means the cosines go away, we just get sine x. And we can take that limit. Sine x is defined everywhere. So at pi over 2, sine x is 1, so that's our limit, just 1. All right, but notice, we had to be able to, it was important to note that this only works because with the infinity over infinity case, I could have rewritten this limit as x goes to pi over 2 from the left of 1 over 1 plus tangent x over 1 over secant x. There's my 0 over 0. Now both of those go to 0, the top piece and the bottom piece. So since we have this ability to use the reciprocals to get 0 over 0, then we can come back here because we have all those limit laws and work with the infinite cases. All right, let's do another example. Okay, the last example I have is going to use something a little bit new and weird. but it's going to work out fine for us. We have this theorem that says if the limit as x goes to a of the natural log of a function, that's fun, isn't it, is equal to L, then the limit of just the function as x goes to a is equal to the limit as x goes to a of e to the natural log of the function is equal to just e to the L. So we're going to be able to take advantage of this. Basically, this is a great thing if you have exponents in your function that you don't know what to do with. For example, this one. We have find the limit. This is what I want to find. You'll see I split the paper. We'll get to that side in just a second. I want to find the limit as x goes to infinity of x raised to the 1 over natural log of x power. Now that's a mess. It's really a mess. So this one can be done very nicely by saying, okay, well, what happens if we throw a natural log on the inside? If we throw a natural log on the inside, do we get something that works out pretty nice for us? Because if we do, if we can get that limit, then the one we want is just going to be e to that power. And so as you can see, if I put a natural log on the inside, that allows me to drop the exponent down in front of the natural log. Right? That's one of our rules for logarithms. So now I have the limit as x goes to infinity of 1 over the natural log of x times the natural log of x, but that just means the natural logs both go away. Goodbye, they're gone. And if they're both gone, then this is just the limit as x goes to infinity of 1, which is 1. And so for our limit, where we're going to replace the L1 now with that, or the L now with the 1, we get a limit of e. So that's kind of fun. There you go. That's L'Hopital's rule. I hope that you learned something. So have a good day, and I'll see you in the next video.